So in this lecture, I'm going to discuss converse of the Wilson's theorems and some problems on Fermat's theorem. So let us move to the converse of the Wilson's theorem. If n minus 1 factorial is congruent to minus 1 modulo n, so then you have to prove that n is prime. So you know the statement of the converse theorem. If n is a prime number, so we have written n minus 1 factorial is congruent to minus 1 modulo n. We'll move to the proof of the theorem. Let n minus 1 is n minus 1 factorial is congruent to minus 1 modulo n. So this implies n divides n minus 1 factorial plus 1. Here we need to show that n is a prime number. Suppose we assume that n is not a prime. So then the number n as a divisor, that is d. So that is d divides n. So let us cut as equation number 1. So now d divides n, and you know that from the statement of the Wilson's theorem, n divides n minus 1 factorial plus 1. So then we can write so d divides n, but n divides n minus 1 factorial plus 1, then d divides n minus 1 factorial plus 1 by using the relation of transitivity. Since d divides n, then the positive number d is the divisor of the integers in the list 2, 3 up to n minus 1. So therefore d divides 2 into 3 into 4 and so on n minus 1. So this implies d divides n minus 1 factorial. So let us call this is equation 2. Let us call this equation 2 and this is equation 3. So from the equation 3 you can observe that d divides n minus 1 factorial plus 1 and d divides n minus 1 factorial in equation 3. From 2 and 3 we get d divides n minus 1 factorial plus 1, that is from equation 2, minus of n minus 1 factorial. N minus 1 factorial, n minus 1 factorial get cancelled. So this implies d divides 1, which is not possible since so 2 is less than or equal to d less than or equal to n minus 1. So d lies between from 2 to n minus 1. So therefore d is greater than 1. So therefore d does not divide 1, which is a contradiction. So hence we can write hence n must be a prime. So this is the proof of the theorem. Now let us take a note. N minus 1 factorial is congruent to minus 1 modulo n if and only if n is prime. But we know that Wilson theorem states that if n is prime number, you have proved that n minus 1 is congruent to minus 1 modulo n. So converse of the Wilson theorem is if n minus 1 is factorial to congruent to minus 1 modulo n, then you have proved that n is a prime number. So that we can restate the Wilson's theorem. N minus 1 factorial is congruent to minus modulo n if and only if n is a prime. So now we consider an example. So prove that 2 power 340 is congruent to 1 modulo 341. Let us move to solution. Let p is equal to 341. So this can be factorized into 11 into 31. Here a is equal to, you can take 2. So let us take it as this capital P and this is small p and q is 31. So now 2 power 341 can be written as 2 power 11 into 2 power 31. So now we need to find the remainder of 2 power 11 remainder when 2 power 11 divided by 31, and we have to find the remainder when 2 power 31 divided by 11. So now 2 power 5 can be written as 32. 32 is congruent to 1 modulo 31. Since 31 divides 32 minus 1. So this implies 2 power 5 whole square is congruent to 1 whole square modulo 31. So this implies 2 power 10 is congruent to 1 modulo 31. So this implies throughout equation multiply by 2. 2 power 10 into 2 is congruent to 1 into 2 modulo 31. This implies 2 power 11 is congruent to 2 modulo 31. So therefore 2 is the remainder when 2 power 11 divided by 31. So and have to find out the remainder when 2 power 31 divided by 11. So And now 2 power 5 is equal to 32 is congruent to minus 1 modulo 11. Since 11 divides 32 minus of minus plus 1, this implies 11 divides 33. So this implies 2 power 5 whole power 6 is equal to 2 power 30 is congruent to minus 1 whole power 6 modulo 11. So this implies 2 power 30 is congruent to minus 1 whole power 6 is plus 1 1 modulo 11. So this implies throughout equation multiply by 2. 2 power 30 into 2 is congruent to 1 into 2 modulo 11. So this implies 2 power 31 is congruent to 2 modulo 11. So therefore 2 is the remainder when 2 power 31 is divided by 11. So let us call this equation 1. This is equation 2. So from 1 and 2 we can observe the lemma here. By lemma, if a power p is congruent to a modulo q and a power q is congruent to a modulo p, so then a power pq is congruent to a modulo pq. So now from 1 and 2 can observe that, so this can be written as 2 power 11 is congruent to a congruent, that is 2 here, congruent 2 modulo 31, and so 2 power 31 is congruent to 2 modulo 11. Then so where a is 2 power p and q, p into q can be written as 11 into 31 is congruent to where a is 2 modulo 11 into 31. So this implies 2 power 11 into 31 can be written as 341 is congruent to 2 modulo 341. So this implies, so 2 power 341 into 2 power minus 1 is congruent to 1 modulo 341. So this implies 2 power 340 is congruent to 1 modulo 341. So the result is proved.